For our project, our goal was comparing two different neural network architectures by developing a machine learning agent capable of playing Super Mario Bros. 2. We programmed two different neural networks in Python, each using a different architecture, with the idea that it could learn to navigate the levels efficiently while avoiding obstacles and enemies. The idea behind this project is to apply reinforcement learning concepts to a classic platformer, exploring how the different architectures will learn differently, optimize its decisions, and improve over time. Our first step was to find a suitable game, and we chose Super Mario Bros. 2. It's a classic and works well for our idea because of the balance between simplicity and complexity with its multiple actions for Mario to perform. This allows our network to more efficiently determine the correct action while still seeing how well it learns to use Mario's abilities, such as jumping as well as picking up and throwing enemies. This should allow the different architectures to be comparable in more different ways without being overly complicated. Next, we considered options for how our agents would learn to properly play the game. We found an environment for the game that tracks important information about the game state, such as Mario's position, health, and pickups such as coins and cherries within the game. The environment also allowed the agent to use 12 different actions, which we could use reinforcement training to allow our neural network to learn the best action in a given state. These actions are different buttons, as well as a few simple combinations of buttons on an NES controller. These are the actions: doing nothing, simply waiting for the moment with no input; pressing right on the D-pad, which moves Mario to the right; left on the D-pad, moving him left; up on the D-pad, which is used to open doors to progress to next levels; the A button, which makes Mario jump; the B button, which lets him pick up and throw enemies as an attack; combinations to allow Mario to move and jump or move and attack, as well as down on the D-pad to duck, and finally down and A to do a duck jump. Using this, we developed a reward function that would incentivize the agent to make progress through the level by comparing Mario's X position before and after the action chosen. We also decided to make it disincentivize taking damage or losing a life, so any actions that would cause it to do so would be rewarded heavily negatively, as well as giving it a slight positive for each action that was not actively killing Mario. The other parts of the reward function include a bonus for collecting cherries and completing a level or a world. We also had to consider which neural network architectures to actually compare. DNQ Linear seemed like a good choice to start with, as we were very familiar with it. We also chose to use DNQ Convolutional, as it was another we were interested to see the results for, and thought it would be interesting to compare how the methods with different layers would perform. The DNQ Convolution architecture works by classifying images, so by showing it different game states, it will be able to classify them based on the best action for the agent to take next to progress in the game. Once we implemented all this into our Python program, we let it train the DNQ linear architecture for a few hours to see what would happen. Immediately, we recognized a problem in our reward function. The part that rewards an action that does not make Mario take damage was too significant, making the neural network choose a safe action over making any actual progress in the level. It would learn one action that would cause it to not take damage and only continue to use that one more and more as it kept being rewarded. To remedy this, we lowered the reward for staying alive 5-fold. After continuing to train both architectures for a sufficient amount of time, we had our results. We found that the DNQ linear performed significantly worse, even with the tweak we made to try and prevent the agent from spamming one safe action. We found it only ever uses action 8, which is right plus B. This makes Mario run off the very first ledge at the beginning of the level. The other architecture, DNQ Convolutional, did slightly better, opting for a few different options as it progressed the game state. Overall, this resulted in both architectures failing to progress anywhere close to the end of the first level like we had hoped. But DNQ Convolutional was shown to be the more successful architecture for this type of program, making it 152 pixels farther. In the end, we learned a lot by doing our project this way. If we were to try again, we would remove entirely the bonus for a safe action, to prevent the agent from being rewarded too much for not progressing in the level. Another big problem we learned of was that in a platformer such as this, the action that leads to Mario's death happens multiple actions before the last one it does, when it actually dies. The action that caused Mario's death in every case was the one that made him run off a ledge, not the ones it was trying to do as it was falling. We could not figure out a clear solution for this. If we slowed down the actions, it would likely fail against a lot of actual enemies and time jumps. We also considered grouping actions in time sections to positively or negatively reinforce those, but that has problems of its own, not to mention the complexity this would add.